We're on chapter 24. This is the chemistry of life, organic and biological chemistry. So, this is going to be an overview of organic chemistry class and biochemistry that you guys are going to be taking in the future. So, this is just a snapshot of what you're going to expect out of those classes and some things you should be preparing for. Hello, this is chapter 24. Now, this chapter really focuses on how chemistry and biology are bridged together. Now, the most common elements that you're going to see in organic chemistry is carbon, hydrogen, oxygen, and nitrogen. Now, organic chemistry deals with the study of compounds that contain carbon, and then biochemistry deals with the study of chemistry when it involves living systems. Now, when it comes to organic molecules, carbon can make these bonds and it can make four bonds. When it makes all single bonds, they are tetrahedral in shape, and this is from chapter number 8 and 9 out of your book. Double bonds would be trigonal planar, single bonds tetrahedral. One triple bond would be linear, sp2 hybridized. Carbon and hydrogen are most common. Carbon forms stable and strong bonds with many elements, including itself, hydrogen, oxygen, nitrogen, and the halogens. Now, the group of atoms that determine how an organic molecule reacts, they are called functional groups. Now, one thing I want to tell you about the functional groups and their mechanisms, you need to know those. So you need to go ahead and start studying the mechanisms and all of that for class, because that's what we're going to go over, and you need to know that. One of the things that we look at is solubility, because carbon-carbon bonds and carbon-hydrogen bonds, they are nonpolar. Solubility in water is very low for many of the organic compounds. Now, you got organic molecules such as glucose that have polar groups that make them soluble in polar solvents. Now, you got molecules that are longer and have polar regions. They act as what we call surfactants, bringing polar material into aqueous solution. That's where you get into your detergents and your soaps. Now, many of the organic molecules has either acidic groups or basic groups. Carboxylic acids are your most common acids, and then you have your amine groups. Um, they have nitrogen in there, carbon and hydrogen. They're most common bases. Think about it: ammonia, amines. Now, you have hydrocarbons. Hydrocarbons consist only of the carbons and the hydrogen. They are grouped based on the number of carbons that are there between the atoms, carbon atoms. There are four basic types. You got alkanes, alkenes, alkynes, and then you got your aromatic hydrocarbons. Those are the four major groups. Four major groups. Remember that. Now, right here, this chart right here will tell you this is nomenclature. And with nomenclature, you need to know them. Now, when you go up in nomenclature from one carbon all the way up, you can see that the boiling point increases. Now, make sure that when you're preparing for next semester that you learn this nomenclature. This is very important. Now, some of the simple alkanes that are out there: methane gas, that is lab gas; propane and bottle gas, heating and cooking fuel; and butane, those are in butane lighters. Use those in fuel campers, canisters for camping. And then alkanes with 5 to 12 carbon atoms is used in gasoline. Now, there are different ways for writing structures in organic chemistry. We're going to get into a lot of those when you guys take organic if you're taking it. Structural condensed formulas don't always show all the carbon hydrogen bonds. They condense them into groups like methyl group CH3. But there are different ones, and you guys got to even know how to write the skeletal structures, so you will see those a lot later. Structure of alkanes. Carbonate alkanes are sp3 hybridized. They're tetrahedral and have 109.5 bond angles. Most of them are straight chains or continuous. The compounds with the same molecular formula but different connections are called structural isomers. We're going to see those next. So butane, 2-methylpropane, that's isobutane, pentane. You can have isopentane, and you can have neopentane, which is the same as 2,2-dimethylpropane, and they have different isomers for those. Now, the way that you write nomenclature, and when you get in organic chemistry, the nomenclature is going to get a lot more difficult because there are different ways, but the basic of it is this. You have the base, which is how many carbons. The prefix is basically what substituents, and then the suffix tells you the family, what type of compound it is. So you got how to name it. You find the longest continuous change of carbon atoms, number the chain from the end nearest the first substituent encountered, and then you name each one. So you can have, here is just a chart: methyl, ethyl, propyl, butyl, isopropyl, butyl. You will see a lot of those, and you'll see a lot of those in the lab next year. Therefore, you can begin with the name, the numbers of the carbon atoms to which the substitute is bonded. To a more substitute are present, you list them alphabetically. Now you can have cycloalkanes, and they form rings or cycles. They have to have at least 3 carbon atoms, but sp3 hybridization will require 109.5 degrees. It's not very stable. Now, 4 rings are also not very stable, but the 5 ring have more room for proper bond angle. And what you have to do is add cyclo as a prefix to the alkane name. So you got cyclohexane, cyclopentane, cyclopropane. Now, alkanes can be unreactive due to the lack of polarity. Now, but for most of them, alkanes are combustible. So when you react alkanes under the presence of oxygen, you will get carbon dioxide and water. Now, you can have saturated and unsaturated hydrocarbons. Now, with the single bonds, they are called saturated. Alkenes, alkynes, and aromatic hydrocarbons have fewer hydrogens. They're called unsaturated. They are more reactive. Keep that in mind. They're more reactive. Now you have alkenes. Now alkenes have a carbon-carbon double bond. They don't have free rotation, and they named the same way you named the longest chain, and they end in E-N-E. If you notice the name of all the functional groups, the ending of the name will tell you what it is. Alcohols, O-L. Alkanes, A-N-E. Alkenes, E-N-E. Ketones, O-N-E. Acetone is a ketone. Normally the ending, the suffix of the name will give you the name of the group it is. Now with these, there are no rotation around that double bond, so you have geometric isomers. They can be cis or trans. Cis means same, trans mean opposite. Keep that in mind if you're going into organic, cis, and trans. You need to know that. Now, your alkynes have the carbon triple bond. They're unsaturated. And they end in YNE. YNE. Now, they have different types of reactions. Now, I talk about this in organic chem all the time. You have these pi bonds are broken. They form these sigma bonds. You can have hydrogenation, hydrogen halides of water, that's HX, or halogenation when it just added halogens. So you're going to see, you're going to hear about these reactions all the time. Halogenation, hydrogenation. You're going to hear those all the time. Now, your aromatic hydrocarbons, this is dealing with benzene. They have a pi ring. It's more stable than the pi bond. They must less reactive, but they undergo substitution reaction, not addition reactions. So that's what happened to them. So you can do nitration, halogenation, alkylation is different ones for that. Many of the aromatic compounds are known by their common name. Others are derivative of benzene because benzene is the basic one. Now, substitution depends on the positions. If they're in 1, 2, they're ethyl. If they're in 1, 3, they're meta. And then if they're in 1, 4, it's para. Now, is a lot of these you have seen, heard of. You heard of naphthalene. That's the mothball smell. Anthracene, toluene. You have heard of those. Toluene is the same thing as methylbenzene. You have seen those in the lab. And these are the functional groups. This is what you need to learn. The main functional groups. These are very important. The chemistry of the organic molecule depends on the functional groups. Learn them, know them. If you're going into medicine, if you're going into anything medical related, you have and need to know these. So there are different ones. There are charts there. You will see charts later on. Alcohols contain that OH group. We also call it the hydroxy group. It ends in OL. So alcohol, phenol, propanol, methanol, ethanol, OL. Now, what do people use ethanol for? Uh, Methanol is used as a fuel additive. Um, Ethanol is basically alcoholic beverages. Uh, Ethylene glycol is in antifreeze. Glycerol is a food moisturizer and cosmetic skin softener. Phenol, it makes plastics. And then cholesterol is a biomolecule in membranes, but can precipitate to form gallstones or block blood vessels. Yes, cholesterol is also an alcohol. Something you'll learn. You got ethers. They form by dehydration between alcohol molecules. They're not reactive. Most of the time, they use them for solvents. Diether ether, THF. Diether ether is one you're going to use in the lab. You got groups that contain the carbonyl group. That's carbon double bond O. And you got different ones. You got aldehydes, ketones, carboxylic acids, esters, and amines. They all have those carbonyl groups. Now, aldehydes and ketones have one hydrogen atom attached to the carbonyl group. Ketones have two R groups attached to the carbonyl carbon atom. Testosterone, acetone, methylethyl ketone, those are ketones. So that's what you see there. Propanone is the same as acetone. So acetone is the simplest ketone. Now aldehydes, formaldehyde and acetaldehyde, uh, those are aldehydes. So formaldehyde is the simplest one. We use that in the lab to store biological samples in. Aldehydes are natural flavorings. So vanilla, cinnamon, spearmint, they come from aldehydes. Ketones are used extensively as solvents. Acetone is one of the ones we use a lot in the lab. Then we have hydroxylic carboxylic acids. Carboxylic acids is actually made from a redox reaction of alcohols and some aldehydes. They are used in a lot of things to make polymers for films. They're used in fibers. They're used in paints. The possibilities when it comes to carboxylic acid sometimes are endless, but that's mostly what they are used in. Then we have esters. They are the products of the reactions between carboxylic acids and alcohols. Now, these are found in fruits and perfumes. Now, you name the alcohol part of it, and then it's a alcohol name, and then it have ATE at the end. So, ethyl butyrate, ATE at the end. Now, when you take an ester and put it in the presence of an acid, catalyst, and water, it decomposes to that. Uh, this is called a reverse reaction to preparation. It's in equilibrium. And so this is called sulfonication, basically making soap. If you heat an ester in the presence of a base, you are basically making soap. Now, amines contains nitrogen in it. Amines are organic derivatives of ammonia. One, two, or all three hydrogen atoms can be replaced by R groups. Remember, that's trigonal pyramidal. If the hydrogen in NH3 or amine is replaced by a carbonyl group, an imide is formed. So if you take the N and attach it to that carbonyl group, you make an amide. Now, one of the things that you have to deal with is chirality. Carbon with four different groups are called chiral. They got optical isomers called enantiomers. They have the same physical and chemical properties. They can rotate. They are plain polarized light in opposite directions. That's what they can do. Now, many drugs that are used are chiral compounds that have equal mixture of enantiomers called a racemic mixture. Often only one enantiomer is clinically active. The other one can be inert or can be harmful. And we talk about a lot of that in organic chem because when it comes to certain drugs like acetaminophen, acetaminophen in an S configuration can be good for you, but if you take it in the R configuration, that one is poisonous and toxic to you. There are different examples of that. Then we got biomolecules or biopolymers. Now, they are large biomolecules built from small molecules. We got proteins, polysaccharides, nucleic acids. Lipids are biomolecules, but they are not polymers. You got amino acids and proteins. Amino acids, amino, have amine and carboxylic acid functional groups. Proteins are polymers of alpha amino acid. Condensation reaction between them produces this peptide bond, and that peptide bond is an amide linkage, the DE on the end, IDE. And so these are natural amino acids. Now, amino acids is something you have to learn in biochem. We're going to touch on it in organic, but you need to learn those in biochem. You have different protein structures. The primary structure is a polypeptide and a protein chain. You have your carboxylic acid group. You have your amine group that is on there. The tertiary structure is intermolecular. You got a quaternary structure that has arrangement of multiple units, and it incorporates sometimes non-amino acid portions of the proteins themselves. And this is how that looks. The primary structure, and you can have the formation of the amide between the amino bonds. It repeats many times, and there's a lot of different ones. There are 21 amino acids. Only one of them is chiral, and you're going to learn about that when you get into biochem. They have secondary structure, so you got primary, secondary. You look at the alpha helix, and you also look at the beta sheets. We talk about that a lot in there about the structures. Now, the beta sheets are pleated regions looking like the shape of a pleated skirt. Now, your tertiary structure, they have side chains with other surrounding in the environment. Usually it's aqueous in nature. Those forces we call intermolecular because that's what drives it. Now, the side chains have polar, nonpolar, and charged groups. Those are the three types of amino acid: polar, nonpolar, charged. They can give you different types of interactions that you guys have actually learned in general chem: ion, 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 dipole, 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 and dispersion forces. The quaternary structure is sometimes made of more than one polypeptide chain. Some proteins are not amino acid in nature. The combination of those subunits are called quaternary. Now, you can classify proteins based on their solubility. Very familiar. You got globular and you got fibrous. Now, globular proteins are roughly spherical and dissolve in aqueous environments. Fibrous ones are usually long fibers and they are insoluble in water. And most of the time, they're used as structural materials. Carbohydrates. Let's talk about simple sugars. They are simple ones. That's how they look right there. Simple sugars or monosaccharides are often drawn in chains, but they are mostly rings in a solution. So the one that we talk about a lot in biochem is glucose. So you got alpha glucose and you got beta glucose. So we talk about those a lot. Now, simple sugars are polyhydroxyaldehydes or ketones. They're often drawn at chains, but most frequently exist as rings in solution. Now, monosaccharides, the most common ones are glucose and fructose. Now, glucose is an aldehyde, fructose is a ketone. So that's the difference between the two right there. Basically, an additional OH group. So that's what you see. Basically, difference is, yeah, OH group, a couple of H's. That's the difference. So one is an aldehyde, one is a ketone. You got disaccharides, and that's dehydration between two monosaccharides creates a disaccharide. So sucrose and lactose are disaccharides. Now, disaccharides are often referred to as sugars. And like I said, we talked about this a lot in detail in biochem. Now you got polysaccharides, and if you dehydrate more, you can make these long chains. You got starch, glycogen, cellulose. Starch consists of many different sizes. Glycogen is animal starch because it's temporary energy storage in animals. The cellulose is a structural polysaccharide. Um, in plants, it makes up the cell wall. It is unbranched. And these are some different types of polysaccharides. Then you have lipids, and lipids are a broad class of nonpolar biomolecules. They're grouped because they're insoluble in water. They are used to store energy, like fats and oil, and for biological structures, and those are phospholipids in cell membranes. Fats and oils are made up of long-chain carboxylic acids and glycerol. Fats have only saturated carboxylic acid. These are called bad fats when it comes to your diet. Oil have at least one unsaturated carboxylic acid. They are liquid. The more unsaturated, the better for you. Polysaturated versus monosaturated. Essential fatty acids with double bonds must be included in our diet. Those our bodies can't produce them. They're called omega-3 or omega-6 fatty acids. Like we say, eating a lot of fish to get your omega-3s, like from salmon, that's where you get those fatty acids. Then you got your phospholipids. Their structure is similar to fats. They're glycerol with ester linkages to two fatty acids instead of three. Um, where are they different? Why do we care? One of them has a phosphate ester linkage connected to a charged polar group, such as choline. They're clustered together in water. The polar regions point toward the water. They can form what we call a lipid bilayer, and the lipid bilayer is the start of the cell membrane. And then this is just a comparison of phospholipids to fats. And then you got the last thing, your nucleic acids. These are biopolymers that are chemical carriers of genetic information. There are two types, and you guys have heard of these before. Deoxyribonucleic acid, DNA, and ribonucleic acid, RNA. Now, what's the difference between the two? There's a lot more, and like I said, you'll get into it in biochem. Now, DNA is the primarily in the nucleus of the cell. It stores genetic information, uh, specifies which proteins in the cells can synthesize. RNA is smaller, is outside of the nucleus. It carries stored info from DNA into the cytoplasm, and information used in protein synthesis outside of the nucleus. So that's the difference between the two. It's a lot more in depth and intel than that, but that's the main differences. These are the structures. Nucleic acid consists of a 5 carbon sugar. It can be ribose or deoxyribose. It has a phosphate group, a nitrogen group, and those one of those bases there. And then polyonucleotides form the condensation reaction between a phosphate and a sugar, mostly an OH group. And then anyway, DNA, double helix, nucleotides combine to form familiar double helix form of nucleic acids. There are hydrogen bonding, dipole-dipole interaction, and dispersion forces that double the helix together. They're complementary base pairs. Note the number of hydrogen bonds, not a double, triple bond. Remember that. You guys, that is all that I have for this chapter. Make sure you do your quizzes and everything associated with this. Have a good one.